All conventional thermal power plants are described by the Carnot efficiency limit, but they can be further characterized via the thermodynamic cycle that's utilized to convert the high temperature heat energy into work. There are multiple designs for thermal engines, but utility scale thermal power plants will use one of two thermodynamic cycles, well-proven thermodynamic cycles. Steam plants utilize the Rankine cycle, in which the working fluid is alternatively vaporized and condensed, and Rankine cycle plants include coal, a small percentage of natural gas, and all nuclear. And most baseload plants are Rankine cycle plants in which the steam is the working fluid. And then the second type are combustion plants that are going to utilize the Brayton cycle, in which the working fluid is a gas form throughout the cycle. The Brayton cycle is primarily used in natural gas plants. Most peaking plants are gas turbines, and these are based on the Brayton cycle. So what we're going to look at first are these steam cycle plants. The steam cycle is by far the most widely used cycle to produce electric power, in which some source of heat is used to boil water and produce steam. The steam is pressurized, and the high pressure steam is then used to spin a turbine connected to the rotor shaft of the electric generator. The basic steam cycle can be used with any source of heat, and this is the process utilized in coal plants, some natural gas plants, nuclear fission reactors, concentrated solar collectors, and some biomass units. In the steam generator, a fuel is combusted in a furnace, or often called the boiler, because its purpose of the furnace is to burn fuel to boil water. So some people call it the furnace, some people call it the boiler. The heat generated via the combustion in the furnace is transferred through metal tubing inside that furnace, heat exchanger, into the working fluid, which is typically water. In this step of the conversion process, energy is lost both to incomplete combustion of the fuel. We see some ash comes out of the system, and then there's also waste heat that gets exhausted from the system. So there's a lot of energy loss in this part of the cycle. Typically, this water is circulating in the boiler. It's then converted into high pressure, high temperature steam. The high pressure steam is then allowed to expand across or through a set of turbine wheels that spin this turbine, and this turbine is connected directly to the generator shaft of the AC machine. That turbine that we've represented here can be a single high pressure unit. However, more commonly, there's multiple units, each with a different pressure rating. So you have a high pressure, high temperature, highly efficient turbine. There'll be increasing number of stages, lower temperature, lower pressure stages, so that you can capture more of that energy. Once it is inefficient of both temperature and pressure to even turn a turbine, the spent steam is then drawn out of the last turbine through a vacuum action by the condenser, which is a unit that converts the water back into a liquid state. It is still steam when it leaves here. The condensed steam, or I guess water in this case, is then pumped back to the boiler to be reheated. The heat released through the condensation of the steam has to be removed through a secondary heat exchanger inside of the condenser. This is usually the cooling water for the secondary condenser is drawn locally from a river, lake, or other large reservoir. Alternatively, cooling towers can be used to transfer the heat directly to the atmosphere, although due to the thermal mass of air, this is a far less efficient process. So most natural gas and nuclear plants will actually use large natural bodies to provide the cooling in the condenser. They do typically eject that. It's not a closed loop, it's an open loop system where they're drawing cool water from the lake, river, or other reservoir. They do typically eject that at a high temperature. So that is one effect. One often overlooked effect of the steam turbine systems is that this condenser unit needs a cool sink. And you can imagine that there's water flowing in this, and then that gets ejected into the river or stream at a much higher temperature than what it was taken in at. So let's do a little bit of math on one of these steam thermal engines. And in this example, what we want to do is estimate the theoretical maximum efficiency that a steam cycle plant can have. We're going to assume the internal steam temperature of the plant to be 600 degrees Celsius and the temperature of the condenser to be 30 degrees Celsius. And we want to then compare this value to actual efficiencies that we know of steam plants. So from the Carnot thermal efficiency limit, we've got N max has got to be equal to 1 minus the difference between the temperature of the hot source and the cold source. And so that those numbers have to be in Kelvin. The temperatures that we were just cited in this example, they were in Celsius, so we have to convert that. That's 1 minus 30. To convert Celsius to Kelvin, you add 273. And then we said that the steam was at 600. It's interesting, right? Steam at 600. How did the steam get to be 600 degrees if water boils at 100 degrees Celsius? Remember, it's high pressure. This is a highly pressurized system, therefore the temperature of the steam can increase plus 273. And we find out that this is 65%. Maximum theoretical efficiency, if we have steam of that temperature, is still only 65%. So, we've already looked at efficiencies of power plants. If you go back to your notes for section 1, you'll recall that we looked at efficiencies, but we didn't do it in terms of percentages. We used a term called the heat rate instead. So remember, the heat rate is 3,412 BTUs. That's the BTU to kilowatt conversion, kilowatt hour, right? So there are just 3,412 BTUs per kilowatt hour. We don't know the heat rate of this plant, but if I divide maximum heat rate by heat rate of the plant, I get its percent efficiency, which is 65%. That means X in this case is going to be 5,249 BTU per kWh. And if you recall, or even if you don't recall, if you go back to your notes for Module 2, or Module 1.2, excuse me, we know that the average tested heat rate of the U.S. steam fleet for coal generation is 10,400 BTU per kilowatt hour, so roughly half as efficient as the maximum theoretical limit, right? A higher heat rate is less efficient, right? You want it to be closer to 3,412 BTU per kilowatt hour. The average tested again being 10,400, so about half of this, so about 32% efficient is average, so much lower than the theoretical maximum efficiency that we could achieve as predicted by the Carnot efficiency limit.